Let's talk about tangent line problem and the definition of derivatives. So the first time you hear about tangent line is probably in geometry class, in which you learn about the tangent line to a circle, like this picture, like the one shown in this picture. The tangent line touches the circle at exactly one point and does not cross through the interior of the circle. You may say that for any curve, a tangent line touches the curve at exactly one point and does not cross through the curve. Is this necessarily true? I used the curve y equals to x cubed to show that it's not necessary. These two properties of tangent line may not necessarily be true. So if you draw the tangent line of y equals to x cubed at x equals to 0, you can pretty much see that the tangent line is simply y equals to 0. This y equals to 0 crosses the curve at x equals to 0 because you can see that the curve y equals to x cubed is negative for x less than 0 and positive for x greater than 0. A tangent line can also intersect a curve at another point. So in this picture, the tangent line, the straight line is tangent to y equals to x cubed at 1, at x equals to 1. This tangent line again intersects the curve at -2, -8. So these two properties of tangent line are not true, and we have to find a rigorous definition of the tangent line to a circle. In order to do so, mathematicians introduced the idea of secant line. Secant line is basically a line that connects two distinct points on a function f. So here's the definition. Given a function f, a line connecting a f of a and b f of b, where a and b are not equal, is a secant line of f, like the one shown in this picture is called a tangent line of the function. So let me show you a program about secant line. In this I created this program in Desmos, and I used the function f of x equals to 1/2 x squared plus 4x plus 1. I fixed the point a at -3.5, f of -3.5, f of -3.5. I call this point a. Then I set a moving point b, a f of a, and I can change the y coordinates, x coordinates of point b. The purple line in this program is called a secant line of f of x. And consider if you move b closer and closer to a, what will happen to the secant line? So you can see that b cannot overlap with a, but if it's really close to a, then the secant line pretty much looks like the tangent line at point a. So we can say that for a function f, and it's not necessarily the one demonstrated in this diagram, if a moving point gets sufficiently close to a fixed point, then the secant line passing through that moving point and the fixed point will also be very, very close to the tangent line of f at point A. So here comes the definition of a tangent sine. The tangent sine to the curve y equals to f of x at point P, P which is a f of a, is the line through point P with slope m equals to the limit of x approaches a of f of x minus f of a over x minus a, as long as this limit exists. So if this limit does not exist, then there's not a tangent line. There isn't a tangent line at x equals to a for f of x. And this slope of tangent sine of x at x equals to a is just the derivative of f at that point. So we denote the derivative of f at x equals to a as f prime of a, and this limit is identical with the one above. So there's another equivalent definition of derivative when we rewrite x minus a as h. So what will happen to this limit? As x gets closer and closer to a, h gets closer and closer to 0, and since x minus a equals to h, we can say that f of x equals to f of a plus h, since x equals to a plus h. So here's the other equivalent definition of derivatives. In future problems, you need to be able to compute the derivative of f of x at a given point proficiently through both of these definitions. So now I'm giving you two practice problems. I recommend you to pause this video here. Try the problem on your own first before I show you how to solve these two problems.